how does this work?
Advance. Big button moves forward, bottom one moves backwards, and if you hold down the very top button, that's how you get the pointer.
I see. Yeah. Excellent.
All right.
So the next speaker is Ricardo Gómez Aíza from Instituto de Matemáticas de la UNAM in Mexico.
Yes.
And he will talk about trees with flowers.
There you go.
Very nice title.
Excellent. Thank you so much. Thank you to the organizers, Daniel, Steve, for organizing this conference and for accepting this talk. I hope it will be pretty easy. And let me cut to the chase. And at the end, I will try to give some motivation. Okay, so trees with flowers. We're going to talk about trees. Trees are things that look like this. We're going to be dealing only with rooted plain trees. And here there is a parameter K that is a subset of the positive natural numbers are the number of descendants, allowed number of descendants. For example, for K equals 1, yeah, we have only paths, 2 trees, binary trees, and all the trees, no restrictions whatsoever. Okay, so those are the trees we will consider. And now let's talk about flowers. There will be 2 types of flowers. They look like this. So there will be rooted plain flowers. These are graphs like this, and you pick a petal, and then you read the size of the petals clockwise. So the rooted plain flower is completely determined by a sequence of positive numbers. So we are just talking about integer compositions, right? And on the other side, on the other hand, this is funny, this control. We have non-plain flowers. So all flowers are equal modulo the action of the symmetric group on the number of petals. So non-plain flowers are just integer partitions. So we are just attaching integer compositions and integer partitions to the vertices of the trees, right? So we're going to denote by F to the N. N is the allowed sizes for the petals, right? Or summands, if you want to think about compositions and partitions. So we will have generating functions for our set of flowers, which will be this the generating function of f of c, generating function of this class f to the allowed number of. Okay, is this clear? I hope so. Yeah, it's kind of easy. So we want to count these type of things. Okay. As I said, I will try to give a motivation at the end. There will be, we will consider the 3 classes of trees with flowers. The first one has flowers only at the leaves. The second one has flowers everywhere but on the root. And the third one has flowers everywhere. So here are the specifications. It's pretty easy. And you can solve these functional equations that you obtain from translating this into generating functions for when the parameters n and k are nice. For example, if you have no restrictions, we have these 3 forms of generating functions in terms of your generating functions of sets of allowed flowers. And for these 4 cases that I mentioned, paths, 2 trees, binary trees, and all the trees. Now, let's consider parameters. Here we are. So suppose you have a parameter on the set of flowers. That one you can extend by addition to the whole set of trees with flowers. Like, for example, count the number of petals in a flower. So if it has 5, then you have your whole tree, you count all the petals. So whenever you have that, if f sub u is the cumulative generating function of kappa, your parameter in the class of flowers. You are interested in the cumulative generating function omega in the whole class X of trees with flowers. So omega, you can also from the previous slide, you can get the cumulative generating functions for the 4 cases in terms of f of z and the cumulative generating function f sub u of z. So with this information, we want to know how the coefficients grow. So in these 3 cases, you cannot see it here, but these 3 are together, and this is white. Also here, because there are different techniques that you use to analyze these functions. If you observe carefully in these 3 cases, we have a dominant singularity of the square root type. It's very simple. And we call, in these 3 cases, for each, we look at what's inside, and we call that P of Z. And for the original generating function and its cumulative generating function, of course, this P of Z is the same, because this is just a differentiation of that. So for these 3 cases, we just do standard function scale, you know that? And we can easily deduce the asymptotic behavior of the coefficients. So if you have these sub-exponential factors, you can deduce the asymptotic growth of your trees with flowers, of the cumulative generating functions of a parameter, and then the expectation of the.
Stupid question.
Yeah.
What is n?
N.
Total size of partitions plus the size of the tree.
N.
N.
Ah, yeah, the size is exactly what you said. Yeah, the sum of everything, all the number of the edges, the number of edges in the. Yeah, I'm sorry, I forgot to say that. Yes, of course, that's what it is. Yes. All right then. So this is an easy theorem, as you know. What is it? I'm getting confused. So this is for all the trees. Then for 2 trees. I mean, the expressions really don't matter. I mean, here's the idea, right? Then 1, 2 trees. I know these are binary trees, and then the 2 trees. Yeah, and I haven't talked about specific parameters. So we consider the number of petals, and you can obtain the bivariate generating functions easily for this. So I don't know if you know, but if you count flowers, the number of petals, apparently they follow Fibonacci kind of like pattern, you know. So like there are no like petals of flowers of, well, that's what they say. That doesn't matter. And then the size of the petals, right? Like for example, this is a flower with very tiny petals, and this is huge, right? I don't know if you see the hand over there. There is a hand, so that's a huge flower, right? So for example, in this tree, this flower has size 19. This has size 17. Here, this flower has 8 petals. So these 2 parameters, we will look at them. And of course, the previous theorem that I mentioned gives us answers for the parameters for these 3 cases. Let's look at this case. That is when we have a path and we put these flowers on the edges, on the vertices of the path. And all right, then. So while here the expressions, I don't know if you can see, they are kind of like f of u over 1 minus z. For example, if f will be meromorphic, if and only if f of z is meromorphic. And for the cases that we are looking at, we have answers, right? So for example, if we have flowers only at the end and the petals the size of the petals are fixed. This is pretty easy. We have we have the asymptotic growth for R, for the omega, and the expectations for the two parameters I mentioned. When N possesses at least two elements, I mean, all these theorems are when we can solve things, of course. Makes sense, right? So when N possesses at least two elements, for example, here, and we are still in the class R, so there are flowers only at the leaf. When we have at least two elements for the sizes of the flowers, we have expressions for the original function, for the cumulative generating function, and hence for the expectations of these parameters that I mentioned. The same for the class S. We have flowers everywhere, but on the root, we have expressions. When we have flowers everywhere, we also have information about the asymptotic growth and more. And what is this? Again, R, and well, there are many cases, right? I don't want to fill in details on the cases. I just want you to get the idea. Here, flowers are non-plane, so that means we are attaching integer partitions. That's why I drew this flower in this way. First the ones, then the 6, 2 6s, and 1 9, whatever. Okay. Excellent. So we looked at the online encyclopedia of integer sequences for all these cases that we got, and we found some of them. There are plenty that are not still registered. This is for k equal n, 2 trees, and if it's green, it means that in the OIs, it's not, there is no register on the asymptotic growth of the corresponding function. For 1 to trees, and look, and for paths, almost everything is known. Well, a lot of it. And I highlighted these two cases because in these two cases, I mean, as you saw, I only used standard function scale analysis. In these cases, you need to use Mellin plus saddle point method. But all these results are already published in the journal of the Bulletin of the Mexican Mathematical Society, and it does not include this type of techniques, Mellin plus saddle point. But we could attach other type of flowers. And for that, let me just point out this paper that I did with Mark and his student Lida. We studied a big family of partition functions that have this horrible expression. I'm not going to talk about this. I would need a lot of time. So, but we can attach here the objects that we study are young tableau with colors and labels. So you can imagine the flowers now, they could have all these funny things. And I need to give a motivation. And here's here comes the motivation. This type of graphs are called petal graphs. And I mean, is that occurs in all this is motivated by in symbolic dynamics from the classification of Markov shifts. Usually you have a Markov chain, and I was talking about the irreducibility. So if you have an irreducible Markov chain, here you are, you pick a vertex, and you look at all the first return loops to your state. So you will obtain a graph like that. And it turns out that studying the classification of these objects can be reduced to study Markov chains with this type of transition probabilities. So when you have something like this, you call lambda if lambda is the smallest positive root of this thing, then log of lambda is called the topological entropy, or Gurevich entropy is the supremum of all the Kolmogorov-Sinaï entropies. It's the variational principle that Anna also talk about it right now. Usually when you have something like this, you truncate it and you work. So you're approximating your system from below, from the inside. So you get a polynomial. And you define a size for the polynomial, which is the evaluated at its derivative. So the set of polynomials with this size function, it's combinatorially isomorphic to the partitions. Is that clear? Yes. Excellent. So so that's kind of like the motivation. We want to approximate these things from below, and here are the we know the why are we doing trees with flowers? Because I mean, these guys did slices of sausages fastened on a skewer. I don't know if you read that in the purple book. So why not trees with flowers? Okay.